What's up, guys? It's me, Sir Ernest, and today we're going to discuss head-on collisions of two objects. Okay, so here, as I mentioned, we're going to look at two particles. Okay, so head-on collision is a kind of collision wherein the motion takes place entirely along a straight line. So that means there is no rotation among the particles, and there's no movement away from the straight line that they are originally moving. That means we are looking at a pure translational motion. Okay, so in this case, from here, again, from conservation of momentum, our equation would become m1 v1 plus m2 v2, and this is equal to m1 u1 plus m2 u2, where m1 and m2 are the masses of the two particles. v1 and v2 are the speeds or velocities of your two particles before collision, and u1 and u2 are the velocities after collision. Here we're going to introduce the parameter called the coefficient of restitution. So the coefficient of restitution is a parameter expressed as epsilon. Usually some books use E, and this is equal to the ratio of the speed of separation. So that means speed of separation, that means the relative speeds of the two objects after they collided. So this is u2 minus u1 over the speed of approach, or the relative speed of approach. So that's v2 minus v1. So the numerical value of the coefficient of restitution depends primarily on the composition of the two particles, especially with the makeup of these two particles. Okay, so we already know earlier that if the kind of collision that we have is dictated on whether the kinetic energy of the system, the total kinetic energy of the two particles in the system, is conserved or not conserved. So we already know before that when Q is 0, so this is your either loss or net gain kinetic energy. If Q is 0, so that means the kinetic energy is conserved, and we call this an elastic collision. In terms of the coefficient of restitution, an elastic collision has an epsilon will be equal to 0. Now, if Q is not equal to 0, so we have a non-conserved kinetic energy, and we now have an inelastic collision. In terms of coefficient of restitution, an inelastic collision can have a value that can range from greater than or equal to 0 to less than 1. As I mentioned before, the value of the coefficient of restitution primarily depends on what kind of particles do you have, the material that it is being used, or the physical makeup of the two objects. For example, a pair of ivory billiard balls, so the one that you use when you play billiards, if if the material that was used to create or to make those billiard boards is ivory, the coefficient of restitution is about 0.95. So that means it's very close to sorry, this should be 1. I'm sorry about that. This should be 1 for an elastic collision. So this should be 1. So again, this should be 1. Yep. Sorry about that. And then, so for example, as I mentioned before, if you have an ivory billiard balls, the coefficient of restitution is about 0.95. So that's very close to 1. So if we have a head-on collision between billiard balls, the kinetic energy is almost conserved. So usually this Q, because it's either energy loss or gain or no energy loss or gain at all, this is usually in the form of a sound, for example. So when you see two billiard balls colliding with each other, you'll hear a sound. So that is a energy that is being released during collision. Sometimes heat is also generated. So this Q can be of any form. Now if, for example, we have epsilon equal to 0, okay, if epsilon is equal to 0, so that means U1 is equal to U2. Because our difference will be 0 and epsilon would be 0. So what does it mean? It means that the two objects after collision is moving at the same speed, in the same direction. So what does it mean? Well, we usually call this they stick together. Okay? So because they're sticking together, we call this a completely inelastic collision. Okay, so an example of this would be your ballistic pendulum, which you have already encountered in your general physics class when you were first introduced with with the concept of collisions. Okay, now in terms of the coefficient of restitution, and when you're going to combine, by the way, again, sorry, if you're going to combine these two equations, this equation and this equation, okay, you can do this by your own on your own time. We can actually express the speeds after they collided, just given the coefficient of restitution and the initial velocities of your two particles, as well as the masses of the two particles. The final velocity or speed of the two objects will be equal to the following equations. So this will be m1 minus epsilon m2 v1 plus m2 plus epsilon m2 v2 divided by m1 plus m2. On the other hand, u2 will be equal to m1 plus epsilon m1 v1 plus m2 minus epsilon m1 v2 divided by m1 plus m2. So again, you can derive these two equations by combining the equation for conservation of momentum and the coefficient of restitution. And finally, in general, for inelastic collisions, okay, because there's energy lost, in terms of the coefficient of restitution, epsilon, this Q is equal to 1/2 mu v squared times 1 minus epsilon squared. Here, mu is what we call the reduced mass, and v is the speed of approach, which is equal to v2 minus v1. So these are your relative speeds before impact. You can derive this from the concept of conservation of energy. Okay, from this equation, k1i plus k2i equals k1f plus k2f plus q. Okay, so that's it, and that's your head-on collisions in terms of the energy lost during collision, as well as the coefficient of restitution. Okay, so that's it. That's all for now. I hope you learned something today, and I will see you guys in the next video. Thank you for watching. Bye bye.